Hello, welcome, and an excellent evening indeed with our second installment of the extended or expanded memory series for Let's Code MS-DOS. As you probably know, MS-DOS was famous for its 640 kilobyte barrier, which meant that you could access only between 0 and 640 kilobytes in a usual MS-DOS program. But even the very first PC by IBM from 1981 supported up to 1 megabyte of RAM in total, which is the maximum that could be addressed directly by the 8088 in the PC and its brother, the 8086, the 16-bit data bus variant. Between the 640 kilobytes and the 1 megabyte would be, for example, the video RAM from the graphics card, the BIOS ROM, and maybe other memory mapped devices or ROMs. With the 8286, the memory size was the maximum memory size was increased to 16 megabytes. However, due to the fact how the 8088 and 8086 addressed the memory in segments and offsets, in the usual startup mode, the 286 could still only address up to 1 megabyte of memory. It needed to switch into so-called protected mode to use the so-called extended memory, which was up to 60 megabytes. The 386 pushed that even further. It had a address space of 4 gigabytes, which probably was never utilized on a 386. All the main boards would never support that much, or probably you couldn't even build or afford a machine back in the day with 4 gigabytes of memory. Same goes for the 486, and so they had just more address lines to address extended memory. So there were a couple of ways to get around this 640 kilobyte or 1 megabyte limitation. And then last installment we saw the expanded memory, which was basically bank switching, which used the blank space between the video RAM and the BIOS to page in or to bank in expanded memory, which could be a couple of megabytes, but you would only see 16 to 64 kilobytes at any given time. The advantage, of course, was that the bank switching was relatively fast. You didn't need to copy anything if you had like a hardware board with this extension. Later machines like the 386 and the 286 could emulate that in software, which was slower because there was the need to copy stuff around, at least partially. And yeah, there were also a couple of other drawbacks basically with the EMS. But the definite advantage was that it was running also on lowly 8086 and 8088 machines. Extended memory, in this sense, after the XMS standard, actually works only from 286 and onwards, and there is even the possibility to do this directly with BIOS support, which for a long time I didn't even know. I also learned this. There are a couple of functions in the interrupt 15, the system BIOS routines, basically. For example, there is a subroutine 88 hex, which gives you the extended memory size in 1K blocks, basically. And the extended memory is everything that comes beyond the 1 megabyte limitation. It only works on 286s and 386s and is basically returning whatever is set up in the CMOS, basically what the machine detected at startup. There's also an extra switch function 89 hexadecimal, which switches the processor to protected mode, which we will not deal with today. We will stick to real mode, but this is also pretty interesting, and you can also do this manually to switch to protect mode. But that's a whole different story. There's also function 87 hexadecimal, which can copy blocks from or to extended memory, depending on which direction you want to copy. It's also a bit difficult to do. and not the normal thing you would use, but instead there is something else called, let's see, XMS, which is a standard by Microsoft, I think, that let's see if there's here's the chapter. The XMS standard by Microsoft, which gives you access to a couple of different areas in the extended memory. First of all, there is the high memory area, which is the first 64 kilobyte of extended memory from 1024 to 1088 kilobytes. And there's a neat glitch in the 8086 design, which means that you can actually access this, the first 64 kilobytes after the first megabyte, even when you are in real mode. No need to switch to protected mode. Also, there is the space between 640K and 1024K if there's free space, and there is memory in that region. It's called an upper memory block, which can also be used, and you can also call or request this via the XMS memory specification driver. And last but not least, it's the thing that we can actually do that we are gonna use, not the extended memory blocks that they're talking about here, but the actual extended memory that you can allocate and copy to and from, which is what we are going to do today, because that is basically the alternative to the EMS. And the main advantage is that you can have, I think, more XMS than you can have EMS. And on 386s and upwards, it's the normal way to access extended memory in software, basically, without having to have special hardware support. XMS is always being done by switching to protected mode, which is pretty fast on 386s. You can switch to and from protected mode relatively fast. On the 286, it is very slow to switch back from protected mode to real mode, because Intel thought that was never going to happen. Their idea was that the system would boot up in real mode for compatibility reasons, so that DOS would still run. But new operating systems like, for example, OS2 by IBM and Microsoft, or some Unix would basically load its kernel and then switch to protected mode and stay in protected mode. They never thought that people would like to run old DOS things as well and need to switch back and forth between protected mode and real mode. So there are some kludges and hacks to switch back to real mode, and running XMS on a 286 can be relatively slow, and EMS can be faster if there's hardware support on the main board. Because basically the 286 CPU gets reset every time you switch back from protected mode to real mode, and that takes a couple of milliseconds, which is ultra long time basically. But we won't concern ourselves with that. Basically, we will just assume that we're running on a 386 and have fast switching, more or less. We will test the program later on a 486 and show that it runs pretty neatly. And we'll do the same program that we did in the MS episode. So if you haven't watched that, you can go back and watch it. Basically loading 35 frames of an animation from the IT crowd into extended memory and copying it into VGA memory to play an animation. And there are a bunch of functions in the XMS driver. First of all, you have to determine if an XMS driver is installed, but once you have done that, you can, for example, query the version number of the driver. You can deal with the high memory area. We won't do that. We will just deal with the extended memory blocks, copying them and so on. We won't deal with the A20 line, which is the trick that you can use to address the high memory area. All that stuff is not very interesting to us here in this place. It's of course of historical interest, and if you want to do real mode programming and have this little extra bit of memory, then yeah, that could be pretty interesting, but we won't use that. We will just concentrate on the extended memory blocks. So let's switch over to the editor and have a look. And here we are. I basically copied the DOS-EMS.c file and changed a couple of names because we are now dealing with XMS. I've already filled out the main function, which is very similar to the old one. I'll skip over the variable declarations. You can look them up when needed. What we're gonna do is clear the screen and then try to initialize the XMS driver. And if it's not found, it will print an error and return. It will also query the version number of the XMS driver and whether the high memory area is available, even though we are not gonna use it. It will print the available memory of the system and also try to allocate enough memory to store all the frames, which is done here, and you can only allocate in 1 kilobyte steps, so we divide by 1024 here, and then it will store the XMS handle if possible. All the XMS functions that we're calling here will have error guarding. Basically, it will do an XMS call and then determine if there was an error or not and print the error. We will implement all the functions one by one, so just be patient. We will come to it in a couple of minutes. Then, as usual, we will load the GIF files by iterating over all the frames. It will also load everything into XMS if possible and copy it over basically by using the copy to XMS function, and do a memcopy of the palette to store the palette basically. Then we will go into graphics mode, set the first palette and do a loop over all the images ad infinitum basically, and copy from XMS into the VGA memory directly, so there's no need to do any drawing, but the driver will basically copy for us into the raw mode 13 buffer, and we'll also set the palette, and hopefully that will do the trick. There will be again a little bit of palette flickering because we are not gonna do the double swapping, double buffering stuff. You can tweak the program to do that so that you will get a perfect neat animation. There's a slight delay of 7 frames, so we will get on a very fast machine roughly 10 frames per second. On a slow machine it will take longer obviously, but there's definitely, before every frame there are 7 refreshes that are being waited for. And if you press a key, you will go back into text mode and free all the memory. So that's neat. Let's go to the top. I've already filled in the XMS error function, so we won't go over that because there's a bunch of error messages and things which are just tedious to type out. Also, I blatantly copied this stuff and reformatted it and made it a bit more into my style from the PC intern book that you can download as a PDF or probably get used at, I don't know, one of the many used bookstores, either in German or in English. Both are available, and I think there's a couple of other languages as well, and they should all have the XMS chapters at least from revision 3 onwards, maybe even older. From version 4 onwards, the XMS chapter is available only on the CD of the book, so your mileage may vary about that. There's definitely something out there that you can pick up. My hint is go to archive.org first, you might find the stuff there, and otherwise buy a nice used copy. Anyway, at the end of the XMS error function, I'm going to check if if the global XMS error variable is not equal to the 0, which means there was an error, and I'm just doing a sanity check. that there is an error between 80 hexadecimal and B2 hexadecimal, which is all the error messages that I got hold of. And then it will just print a readable error message from this array up here, and then it will exit the program. All right. However, there is a couple of other things that we need to introduce. Mostly the XMS registers and the extended memory move structure. Because the XMS driver doesn't use a software interrupt like the BIOS interrupt 15, but actually uses a var procedure call basically, and all the parameters are handed over in registers. It's always the same registers. We have the AX register, BX, DX, and of course I'm using a struct here so I can pass these things around easily, but you could also write assembly language and just put it into the registers as is. But one main issue is, for example, this here, the pointers to the memory in question are passed in DS and SI, and if you just manipulate DS in Turbo C here willy-nilly, the whole program will crash. For example, we'll see how to implement the XMS call itself, and I tried it using the built-in pseudo registers. For example, you can do stuff like _x equals 0, and it will emit code similar to mov x, 0, because this here signifies to Turbo C, okay, the programmer wants to write to the AX register. You can even do something like this, word segment equals _ds, and it will do something like mov segment, ds, for example. Yeah, it will read the ds register, but you can't do something like _ds equals what is it? I don't know, something like my segment, which is a variable or something, which would probably emit something like mov ds, my segment. This will be done, but then as soon as you do something like my var ++ or something, it will crash, because my var will be try to be resolved in the data segment, which you just manipulated. So that's a bad idea. Reading the data segment is okay. Writing to it just like that inside of the C code is bad. So we will use inline assembly later on, which also means that we can't use the IDE anymore to compile, which I'll explain also in a minute. But this is also a reason why we have this register structure to move around all the data that we need for the call. Also, for moving around data, the XMS driver expects a bunch of values. First of all, a 32-bit value, which I call length of bytes, that are supposed to be moved around. A 16-bit value, I could also write word, which is the source handle, and another 32-bit variable called the source offset, because the extended memory, of course, can be bigger than 16-bit or 64 kilobytes. So that's another 32-bit thing. Actually, I think I defined long as double word, so let's just use that. It's, I think, better to read it like that. And then there will be a destination handle, because you don't get pointers to the extended memory, because the extended memory might be defragmented by the XMS driver, so you get back a handle like a number, which is in DOSBox interestingly always incrementing from 1, 2, 3, 4, 5, but in DOS it's basically random. You can't predict what handle you will get back, which you can see on a real machine actually. And there will also be a destination offset. And the idea here is, if using real mode memory handle equals 0. So that means if you have, for example, a source or destination that lies in real mode memory below 1 megabyte, you're not using an XMS handle, but you're giving handle equals 0. And here you're using offset, an offset like segment offset. Basically, you're constructing a far pointer. Otherwise, if this is an XMS handle, of course, you just give an offset just from 0 to whatever memory you allocated. I think this is pretty easy. And as I said, we don't have a software interrupt, but we have a call basically, which is a far pointer to a function. The function we're going to call XMS pointer, a pointer to the driver. It's always the same. And we will initialize it with a null, just to be on the safe side, so that the machine crashes if we accidentally call it before initializing anything. We also need the global error variable, which we'll also initialize with 0, so that it says there is no error yet. And we will need our handle that our program uses, which is also initialized by 0 because we haven't allocated anything yet. Now on to the calling of the XMS driver. Right now we don't even know if there is an XMS driver, but we'll come to that in a bit. But basically what we'll do is we'll use inline assembly, which in TurboC 2.0 works like this. You basically just write simple instructions with the ASM keyword. For example, we will overwrite or destroy all these registers, so we need to move them to the stack to be able to restore them. So first of all, we will save the source index, and just so that my other editors don't get confused, I will put a semicolon at the end, but that's totally optional with the inline assembly, I think. I'll also push the DI register, and I will save the DS register. I will not push it to the stack because I will use it in a minute. So instead, I will save it to the CX register, which is unused in this call. And then I will push it to the stack. This basically, I think push DS might not be possible on an 8086. It might be that this is only possible from 81, 86 and onwards. But I'm not 100% sure. I would have to look that up. Also, I'm gonna put in to the destination index the address of our registers that we've put there basically, which is something like this. This gives us the address of the XMS registers. And into the high byte of the AX register, we will put the function number. And I'm probably gonna switch to English here, function number, which is hopefully a bit more readable. And then we will load up the other registers. The BX register was the second one in the struct that you can see here, word BX, it was the second. So as we have in DI now the registers pointer, we can do something like this. I should use morph here. Nobody told me I forgot the morph. So as an morph BX, comma, destination index +2, because it was the second item, and we are adding 16 bits because we are having we had 16-bit entries here, word AX, word BX, and so on. So this is basically +0, +2, +4, +6, +8, and that's what we're gonna do now. We are just gonna fill up all the registers. The next one was DX, and that was in address DI +4 as a morph source index, in DI plus 6 and DS in DI plus 8. And here it doesn't matter that DS is now destroyed because we will restore it in a minute. But first of all, we are going to do the XMS pointer call, which means that we're gonna load up ES with the value of DS that we saved in CX, for the very simple reason that we can't use CX to use it as a segment register. We have to use a segment register. And now we will just do the procedure call with ES, because DS is already taken by this call here and was destroyed. And CS we can't use. So what are we going to do? We are going to call ES colon XMS pointer, and the square brackets will dereference this segment with the offset of this variable, which basically looks into our global XMS pointer variable and takes whatever is here. Now it's a null pointer, but it will shortly become a valid pointer into the XMS driver, and it will jump into that subroutine and do its magic. After that, we have to get all the return values. For example, we will put whatever was in DS into CX again, because that is also a return value that we got back from the driver. And we will now finally restore DS from the stack. And now we could switch back to C and use all our usual tools that we know and love. But instead, we're gonna do the reverse that we did before. We will load up DI again with the registers pointer and then start reading out all the return values, because the functions will return stuff also in the AX, BX and so on. And the register structure is basically an input and output parameter structure. So we can almost do it like above. We will write to the first variable whatever was in AX, that's a return value, and then we will write to DI plus 2, whatever was in BX, and so on. DI plus 4 will get the value from DX, and DI plus 6, you can guess it, will get the value from the source index register, if, for example, some memory addresses have to be passed around. And the last one is CX. And also we pushed DI and SI from on the stack, and we have to pop them in the reverse order. So pop DI and pop SI. And that's it. That is a complete XMS driver call. Take your time to try and figure out what we did there. The most important thing is the AX value should be 0x00. Or shouldn't, I think. If it's 0x00, we are having an issue here, and the error value that we can look up in our table will be in the BX register. So that will happen. And else there will no error be here below us, basically. So we set the global error variable to 0. Okay, which is nice. And this should actually do the trick, I think. The next function is the init XMS function, which initializes the callback to the XMS driver. And as I said, this is done using a for procedure call and not an interrupt as is usual. However, we will have to use an interrupt to get to this point. So there will be 2 calls here, one with the usual registers and one with segment registers. And the first we'll access the multiplex interrupt, which is an interrupt that gives you access to multiple functions in MS-DOS. And there is the function 43, and let's have a look. The multiplex interrupt is the interrupt 2F, which is here, and there should be a function 43, hopefully. Not really. It's not listed in here. Yeah, but the DOS multiplex interrupt certainly has this feature. And if you look it up, there will be information about function 43. But I think this help PC does only list the standard DOS functions without additional drivers. So yeah, that's not there, but you can just call it and trust me on this. So 2F is the interrupt, and we pass the registers as input and output as usual. And if you get back in the lower register AL the value 0x80, then the XMS driver exists and is installed, and you can work with that. And else you can just return false. Here we can return true, and we have to fetch the address of the driver. We can do that by another subfunction, which is rex.ax equals 0x4310. So this is driver 43 hex is the XMS driver subfunction 0, and this is subfunction 10 hex. And we're doing another call. However, this time we will get back the segment registers as well. There's a special function in TurboC for that. It's called int86x, and it takes the normal registers plus it will return the segment registers exactly for this purpose, basically. And we can construct our pointer, the far pointer, by using the mkfp make far pointer macro. It takes a segment, which we take from the segment registers. The return value is in ES. And we take the offset of the function call, which is in BX. So ESBX gives us the pointer. And then we set the XMS error variable to 0 because, yeah, it was fine, basically. And that's that. Next up, the available memory that we have in kilobytes, basically. And this will be our first proper call to the XMS driver. That will work for all the functions in the same way. We have our XMS registers, quick jump back here. It's AX, BX, DX, SI, and DS. Those are the only registers that are manipulated or used by the XMS driver. And then we do the call. There's nothing to set up, basically. The function is 0x08, so 8 hexadecimal, and we just pass the registers. And then the total amount in kilobytes that is available is in the AX register, and the maximum free block that's still there is in the DX register. So you might have like 60 megabytes XMS in total, but there might be only like 8 megabytes free if, for example, Smart Drive is already using 8 megabytes for disk caching or similar things. And yeah, allocation works similarly. We can do the following. Basically, we can copy the calls as we want. Yeah, let's call this rex dot DX gets the amount of kilobytes that we want to reserve. You can't reserve in bytes, but you always have to deal with kilobytes. So when allocating, you have to round up to the next kilobyte. That's very important. And the function is actually the next function, 0x09. And the handle is actually also returned in the DX register. It's basically the input-output register of this. Let's write this return XMS handle. This is basically just a number, random number on MS-DOS, an incrementing number on DOSBox. That is so that you don't need to use a pointer or anything, but just a number that references to the block that you allocated. Same now for the free. Once we allocated something, we have to also free the thing. I wrote here that I'm gonna return a bool, but I think I'm gonna switch this to a void, because actually we don't return anything. And instead of the kilobytes, we put the handle in the DX register. As you see, the DX is usually the input-output register of choice. And it's, of course, the next function, 0x0a. That's it. Now you can allocate and free memory in XMS. Let's do something easy first before we go to the copy function. Let's do the version. That is actually not that hard. Let's again copy everything. And this time we don't need the register here. The function number is actually function number 0. Very simple. And we get back the digits in AX, basically, in AH and AL. So the version number is in AH, so we could do it like this. We could probably just write okay, we don't have the union, so we have to do it like this. Shift right by 8 bits, whoops, not bytes, bits. And the revision number is in rex.ax. And we mask out only the lower 8 bits. This will give back 3.0, for example, so 3 in the version and 0 in the revision number for DOSBox, for example. And the DX register contains a 1 if I think everything was okay. Oh no, it means, no, that's actually not true. DX equals 1 if HMA is available. Which is not available on DOSBox. DOSBox doesn't emulate the HMA. It's too much hassle, and the HMA is usually only used by MS-DOS itself, so there's no need in DOSBox. But on a true DOS with hymem.sys, this will return 1, which is quite nice. Now off to the copying, because that's the most important thing, so that we can also write the copy to XMS and from XMS. We write a generic variant here, because this one here takes a from handle and a to handle, and if either of those is 0, then the offset is not an offset but a pointer with a concatenated segment and offset address, as usual. The high word contains the segment, and the low word contains the offset. I think maybe the other way around, but I think that's the case. So let's do that. Again, we need the registers. We need the XMS memory move structure, which we call MI. I copied these names from the PC intern book. Then we need a far pointer, which points to the memory. Exactly, for the structure. Then we fill the memory move structure mi len bytes equals the number of bytes that we are trying to copy. That's the input parameter. Mi source handle. Did I call it source handle? No, I called it... yeah, I think here it's called source handle in the structure. I should have used the same identifiers here. It's not very good. You can change that at home. So this is basically the from handle, also the source handle. Not very clever of me indeed. The source offset is the from offset. So nobody has to deal with the outside of this thing with a memory move structure. This is totally internal. And the destination handle is the to handle, and the destination offset is the to offset. Let's do it like this. The pointer points to the structure. We have to use a far pointer here because that's what the XMS driver requires. Then we set up the source index with the offset to the pointer. So this pointer is actually totally optional. You could just write and.mi here, of course, and save this one variable. And the data segment gets the segment address of that pointer. And everything is passed to the XMS driver using function B, which is the next one in line, obviously. All right, that's looking good. This is the copy function, and it's totally agnostic to whether it's copying between XMS and XMS, main memory and main memory, or any combination of XMS and main memory. This will always work, and you will have to pass in the actual handle or 0 if you don't have a handle, because it's main memory basically. And now we can also build the copy to XMS and copy from XMS functions. This is simply convenience. Very, very simple convenience. So we use XMS copy. If we're copying to XMS, we pass the handle 0, and we convert our pointer, our far pointer, into a long just by casting. And we use our global XMS handle that we allocated, hopefully, and the offset, which will be computed depending on what image we currently want to access. It's basically just end image has n times 64,000 as its offset, naturally, because it's 64. Every image is 64,000 bytes long, and that's our offset. And the size is 64,000. But this function is still pretty agnostic towards what we're actually copying, so I'm formulating it like so. Next up is the copy from XMS. There we have the XMS handle and the offset, and then we pass 0 as the destination, and not offset, but I would rather say, oh yes, offset. Yes, offset indeed. But I would rather say the same thing, casting to a long value the destination pointer. And that's the same thing. And this actually should be everything that we need. We have everything else already in place. So when I compile this, it should compile all this stuff here, initializing, printing the XMS version, loading everything and copying everything to XMS here, and then copying from XMS the image into the VGA memory directly. If we were to try and compile this, we will get a whole ton of problems. One thing here, but especially inline assembly is not allowed. And this is what I already said. You can't compile this inside of the IDE because this very old version of Turbo C doesn't support inline assembly. You have to use the command line compiler, sadly, to do that. But it's no big deal. Very quickly to show you, I wrote a little batch file called make.bat, which compiles with the command line compiler TCC, and a couple of optimization options, which compiles for 286, and a couple of optimizations. All the three files that we need, DOS XMS.c, then the VGA routines, and the GIF loader, all into one file. So that's no big deal, but it's a bit more difficult to compile than just hitting compile and build everything. But there was also more issues. Let's type make. Seems we have done a couple of errors, which is par for the course when I do this. Undefined symbol, yeah, that should be easily fixed. In the copy function, I think there's just a mistyping. Here we go. Oh yes, okay. It's probably like that, right? And that should do the trick. Build all will complain about only. There's something. Function number is not used. Did we forget something? Yeah, I think there needs to be the function number that we forgot. That's a good point. Another typo, basically. Yeah, that should be actually, that's actually very, very correct. Oh no, it's not correct. It's just because it doesn't know about the assembly, that's why. Okay, nothing wrong there. Let's compile again. Undefined symbol. Okay, it's still not happy. Non-portable point assignment, yes, that will be fixed. So let's quickly check again. Oh, okay, yeah. We need to capitalize correctly. Building it again. Okay, this is quite nice. And another typo. FPSeg should be FPSeg for segment. Yeah, here we are, FP segment. Okay. It doesn't work. All right, this is looking good. There are no warnings except for restarting compile using assembly and function XMS call, which is totally fine. And then it will call the turbo assembler, which you have to have installed as well, which doesn't come with turbo C normally, but you can download it as well. And it runs turbolink from probably turbo assembler as well. And there we go. So let's start it first on normal DOS box, and then we'll try it out on the 486. And it will take a while. I will fast forward this. You can see XMS version 3.0 HMA is not available, but XMS handler is detected, and we have 15 megabytes in total, because 1 megabyte is base memory and 15 megabytes extended memory, and it allocates 2188 kilobytes in total for our program. That's the 35 VGA images of 64 kilobytes each. And one more thing, the XMS handle is 1. That is also not the case on DOS. And there we go, it works! The video basically is played from XMS memory, and it's decently fast on the emulation. But let's see how it runs on real hardware. Okay, here is the 486 DX33, and it is currently equipped with 20 megabytes of RAM, which is quite substantial. I'm using 4 standard 1 megabyte modules, SIM modules, I think, and also 4 megabyte modules, which we made ourselves in a previous episode or stream, I forgot, which are the kind that Bits and Bolts designed. So we have tons of memory, and as you can see, There is total memory 20 megabytes, 3 megabytes are used. I think part is used by smart drive, I guess, and roughly 17 megabytes free of extended memory. There's also expanded memory, which is simulated by EMM386 using XMS. So there is roughly 8 megabytes of expanded memory here. Let's run our tool. And yeah, it also detected the handler. It is also using version 3.0 of the XMS standard. HMA is available, which is different. And there are 16 megabytes in total, and 60 megabytes is the largest block. And it's trying to allocate the 2187 kilobytes or so. There's still a little bit of debug output here. And we have a random handle of 43282. And yeah, the loading is almost done. The GIF loader is not very performant, but yeah, it works. And there we go, it works. There's more screen tearing here, and the palette is not super synced, but I think part of this is due to the very slow ISA card, graphics card obviously, and also probably the OSSC is not doing a good job of the syncing up with the vertical retrace or something. But yeah, it's definitely a proof concept. This works. You probably couldn't stream this stuff this fast from the hard disk. And as you can see, the GIF decoding is pretty inefficient. So yeah, putting it all into XMS memory works actually quite well. So now you have all the knowledge to produce EMS and XMS memory in your DOS programs, which gives you access to a whole lot more memory without having to deal with all the shenanigans that is protected mode and switching back and forth from protected mode to access hard disks and do DMA transfers on the Sound Blaster card and stuff like that. Maybe we will touch that in a future video, but it's a whole different kind of worms, especially if you code it manually, if you don't use a 32-bit C compiler like DJGPP or Watcom, but if you code this using normal Turbo C or Turbo Assembler, it's a very complicated thing indeed. Not impossible, but pretty hard actually. So we won't be doing that right now. The video has gotten way too long already. So I think it's time to say goodbye and see you in the next video. Share, like, and subscribe, the usual stuff. Patreons usually get this stuff a couple of days early, and also here and there a few more smaller videos or messages. And if you want to join them, you know where to find me. Links are in the video description. Other than that, leave a comment, and I hope to see you in the very next Let's Code video, or the next regular whatever tinkering video using retro computing. I do say thank you and goodbye.